Hello everyone. So I think I'm audible and visible to you. So we will start the session in 2 to 3 minutes. So today we'll be discussing about particle in one dimension box. That's the topic of quantum physics. So these courses which I planned some months ago on special theory of relativity and then quantum physics. These are all the introductory lectures. Okay, so don't treat it as the comprehensive lecture on. It's a comprehensive, but it is not that you will say that it will cover every aspect or every topic, because it is if we consider special theory of relativity, it is a very you can say broad topic. We are just discussing those concepts which make you feel the physics, and also what are the basic requirements, or the just for fun also you can have that to understand the real physics. Because see, we study thermodynamics in physics only. We study thermodynamics, modern physics. There are several branches. We have electromagnetism, we have mechanics. But what I feel, the part of modern physics, mainly where we'll discuss about atomic models, we discuss about more advanced form, that is your special theory of relativity, means relativity, quantum physics. These are the modern aspects or the modern physics. So these are more interesting also, and these are the real physics, because uh, modern physics or the your special theory of relativity, that is under this only. So these make you feel the real, I would say, taste of physics, because physics is not something that is just written in the textbook. We can physics is the only subject. See, I admire physics just for one thing. Rest I don't admire it. The only thing for which the physics is respected is the, you can say, power of imagination. In physics, you can feel the concept. You can see things. You can visualize, because visualization, once you have the visualization, once you have a visual picture in your mind, then solving numericals or understanding the concepts become very easy. This is not given, or this is not provided us in chemistry or in mathematics or any other. That's the I would say beauty of physics. But rest, mathematics is uh, needed in physics. So mathematics is an independent subject. So mathematics doesn't need any other subject to complete, but physics needs. If we remove mathematics from physics, physics will be just like the mobile without internet in 21st century. Not talking about 20th century. Okay, in 21st century, if we don't have internet in our mobile phone, its its value shrinks to zero, right? So that's with the physics. Physics needs mathematics, but mathematics doesn't need physics. Mathematics is complete by its own concepts or its own uh, tools. Okay, so that's because we met nearly 1 month. After nearly 1 month, because there were several things going on. Okay, so I took break. Even I uploaded shorts and I tried something new towards the music because I really admire music. Whenever I'm doing any of my work, I used to play the music, and mainly I like the old songs, not that new songs, but still I listen to new songs also. That's also not that bad. But the old songs I prefer more. So that's why I turned to musical side also little. But still now I am back to the academics and now we will be discussing it. And the lectures will be more frequent and more, I would say, consistent from this particular week. Okay, so today is 18th August. So today we will be discussing about the particle in one dimension box. I hope that everybody has have revised the little having the cold. Okay, so sorry for the inconvenience. So I think you all have had revised the previous concepts, mainly the Schrodinger wave equations and the basics of phase and group velocity that we discussed in the last session. Today, more or less, I'll completely just wrap up this uh, Mahabharat, that is quantum physics, with the last topic, according to me, because I already took the topic hypothesis, de Broglie hypothesis. So this will be the more or less last topic, that is particle in one dimension. Okay, so let me share my screen with you and we will start. Just give me 30 seconds more, okay? By the way, I am unable to provide you the comprehensive notes because I just use different sources, okay? So you can prefer books, okay? You can use books like I think Professor Verma has also uh, written a book on this quantum physics, yeah. So you can see the Professor Verma book. Uh, that is, I think, on quantum physics, okay? So let's begin. So just let me see that whether my screen is visible to you all or not. Yeah, it's fine. So, hello everybody. So let's begin our today's session. Today we'll be discussing about particle in one dimension box. First of all, we will discuss what actually one dimension box is. First of all, any box. See, there is a what you say contradiction when we say one dimension and when we are saying box, because any box you see, it can never be one dimensional. Okay. So what does one dimensional box mean? First, we will have a quick discussion on it. Then we will be discussing about the particle in that particular one dimensional box. So the box is three-dimensional or two-dimensional only. It is not one-dimensional. Particle in one-dimensional box is different. Just look at this. Suppose I am drawing a three-dimensional box. We can call it cube also. See, this is not becoming cube, but just manage with this cube this time. Okay. So this is your three-dimensional box. That is your cube. Now, what do you mean by one-dimensional particle in one-dimensional box? When we restrict the motion of particle in any of the two direction out of the three direction possible. See, when we are discussing the cube, we are discussing the three-dimensional space. So in three-dimensional space, we have three types of coordinates that we say x coordinate, y coordinate, and z coordinate. Now, when we have a particle whose motion is been restricted to a single direction, whether it is x direction, or it is y direction, or it is z direction. Okay, so whether it is x direction, whether it is y direction, or it is z direction, but the motion is restricted to a single direction, then we say that particle is in one dimensional box, because the box is really box is indeed the three dimensional. It is perfectly three dimensional, but for that particle it is behaving as one dimensional box, because the motion has been restricted in two different directions. Suppose we restrict the motion in y and z direction. Suppose we restrict the motion in y and z direction. Then what will be the direction of motion of particle? That will be x direction. If we restrict, see here you can't restrict in the single direction. That you will say that the particle can't move in y direction, but it can move in x and z. That is not the concept of particle in one dimensional box. Particle in one dimensional box says that we restrict the motion of particle in two directions, two possible direction, two possible coordinates. Then we will have a single coordinate system left, or you can say single direction of motion possible. So then that particular particle and that particular box act as one dimensional box for that specific particle. It is not always. If we say absolutely, it is a three dimensional box, but relatively, when we are discussing the particle in that particular box, then we will say that it is one dimensional box because the motion is restricted in other two directions. I think this part is clear to you. Okay, nearly 2 to 3 minutes or 4 minutes I took on this because this is very important. This is the first confusion that you have, that whenever you see any box, you will say that is two dimensional or three dimensional. How can it be one dimensional? How can you say a particle in one dimensional box? So yes, we can say this. No worries. The motion is restricted. Okay. The way of explanation changes. Okay. So this is a relative term. One dimensional box is a relative term. In reality, absolutely speaking, it is a three-dimensional box. It is a cube. Okay. Let's proceed further. So Schrodinger equation for one-dimensional box. Our first here point is there. So this we have discussed only, but just for an revision and just for introduction, we can have this again. We are going to use as a concrete example of how to use Schrodinger wave equation and simple system. See, what you have discussed the Schrodinger equation, we are going to apply it here. Okay, this is the application part also. So particle is with the mass m. Now the particle which is in one-dimensional box, we are given with the mass that is small m, and it is confined inside a one-dimensional box of length L. Okay. Now the box one-dimensional box that is there, its length is L. This is not as an interesting example you might think, because when you extend this to a three-dimensional box, we actually are talking about the quantum mechanics of ideal gas. Yeah. So when we just extend this discussion from one-dimensional system to the three-dimensional system, then we are actually discussing about the quantum mechanics of the ideal gas. As you know, ideal gas, some of the properties is like they have the what do you say? No, I forgot. Uh, no intermolecular force of attraction, like that it is negligible. Yeah, so that's, you can check on it. In order to solve the wave equation, for the wave function psi of x, we need to write down the correct potential energy function and identify the boundary condition. This is very important. Actually, when we are talking about the boundary condition, it is actually the comprehensive topic in higher mathematics. Boundary value problems that are considered one of the toughest problem of in the higher mathematics. Boundary problems. Okay, boundary condition problems. So, but that is not that tough also. But here we will have just introduction. We'll identify the boundary condition. You have to just assume here boundary condition as the limits. You study the integration. You have the upper limit, lower limit. That is not the boundary condition actually. That is upper limit, lower limit is the boundary condition. But you can relate it in that way. For simplicity, potential energy and boundary conditions. We start with this particular topic. For this case, we are going to assume that particle experience no force on it. Okay, so there is an assumption. See, each and every concept in physics mainly is based on assumptions. If we remove the assumption, if we just consider the real world physics, the modern physics is also not the real world physics. Several assumptions are being taken while explaining this particular concept. Here, the first one is there that we have to assume that particle experience no forces on it. While in the box, so that means potential energy is a function of x and it should be constant anywhere in the box. See, suppose this is your x is equals to 0. Okay, this is your x is equals to L, because the length is L. So inside this particular box, the potential energy, which is the function of x, is constant. Is constant for the x belongs to 0 to L. Inside this region, not on the boundary, not on the this boundary, but inside it. Okay. However, we need to keep that particle confined into that box to make the potential energy infinite. See, for this x is equals to 0 and the less than this portion, this area, including this as x is equals to 0, the potential energy is tending to infinity, is going towards infinity. And for the x at L and the greater than L, the region, this particular region, see, there are three regions: inside the box, outside the box. Outside the box also we have, if we consider x is equals to 0, then outside this, but the you can say region outside x is equals to 0, but not containing in the 0 to L, open 0 to L, I would say what, open 0 to L condition. Okay, open 0 to L region, sorry. And this is x, this is the second one. Okay, so one we have the inside region and we have the outside region also. So in the outside region, including x is equals to 0 and x is equals to L, the potential energy is going to infinity, and we assume, and or you say we will set the potential energy equals 0 inside the box, that is from x belongs to open 0 to open. Fine, great. Now the boundary conditions on psi x will be set by what we know about the particle motion. In particular, this we have discussed that as we set the boundary conditions on this particular potential energy. Okay, that we have assumed that for this internal regions we have the potential energy 0, and for the outside region we have infinity. So that's why psi of 0 at this particular, because what is psi? See, particle you are getting inside the box. Particle is inside the box. So what this the significance of psi is? Actually, psi itself does not have any significance, but we consider as psi square, suppose. So the probability density. So when the particle is present inside the box, then the probability density, the psi, will be non-zero only inside the box. So at the boundary condition also, x equal to 0 or x equal to L, that psi of 0 at x is equals to 0 or psi at x is equals to L will also be 0. That's clear from here. Other criterion that we can employ is that the probability density we get from the wave function, that is here we discuss the probability density. I was talking about probability density, that is actually psi square x. Okay, is normalized. We have discussed about, I think, the normalization of wave function. Yeah, so that's this is the so that the probability of the finding the particle somewhere in the box is unity. Means we made the normalization such that inside the box, wherever we take, we get the particle. We find the particle, or we are able to find the particle, because the probability is what? The probability is can be 0, can be 1, or between 0 and 1. So if probability is 1, the probability is 1 means you have the 100% chance of getting that particle. That is here actually discussed here. So this 0 to L, if we integrate this probability px, that is psi square x over the dx, then we get the 1. Okay, this is normalization we discussed earlier also. So this is your figure. Okay. Okay, just give me 2 to 3 minutes. Okay, we will continue. Yeah, I'm back. So let's continue. So this is the graph. Okay, potential energy function for a particle in one dimensional box. So this is, and this on the y coordinate, u of x is is been plotted, and in the x coordinate, the position function is plotted. So as you can see, this is 0 at x equal to 0, and this is x equal to n. So the same figure I through that I explained here also. That's the same one. Okay. So solution to Schrodinger equation. So now we will have little derivation portion. So with these conditions in mind, whatever we have discovered, that inside the box the potential energy will be 0, and considering these regions outside it, the potential energy will go to infinity. And then we discussed also on the boundary conditions on psi of x, and also the probability of x using the normalization. So we'll consider all the aspects, and now we will be having the derivation, full and final derivation. Okay, so that we'll be discussing from scratch. So now we can solve the Schrodinger wave equation. Okay, with these condition in mind, we can now solve the Schrodinger wave equation for x belongs to 0 to L. Just look at here. X is belongs to open 0 to open L, means this particular condition, this particular region. Okay, this one. excluding x equal to 0 and x equal to L. So minus h cut square. H cut, I think you know, we have discussed so many times. Reduced Planck constant, which is h over 2 pi. Okay, so minus h cut, this we have already, you can say, derived. Here's the improvised version. It is minus h cut square by 2m, then d square psi by dx square, you can say second order derivative, plus potential energy as a function of x into psi of x is equals to E into psi of x. Then we just uh, made this particular, okay. Inside the box, you know, the potential energy is 0. This factor will go to 0. Okay, this will go to 0 because we are solving for x belongs to open 0 to open n. So then we have this condition, and then we can get the d square psi by dx square as this expression. Okay, so this is just the differential equation of for a simple harmonic oscillator which has the general solution. This, so this particular is a differential equation. You can see how this can be a differential equation. You can use the definition also. First of all, it is a second order derivative, and uh, this is a second order derivative. Also, the degree is 1. So yes, it is a differential equation. So this is actually a differential equation for harmonic oscillator, simple harmonic oscillator, which has the general solution. Simple harmonic oscillator, you can say simple harmonic motion for that pendulum. Okay, for that the psi of x is a sine kx plus b cos kx. That is quite easy here. We can just substitute here, where k can be determined by substituting into the differential equation. Okay, this is a k square. So actually what you have to do, simply psi of x you have, okay, just you have to take the double, this particular first order derivative, then you have to take second order derivative, and then you will get the k square as 2me by h cut square. This is actually the k square. K square. Okay, this k is coming as root under 2me over h cut. Now we will apply the initial boundary condition, that is at x equal to 0 the psi is 0, because the particle is inside the box. The probability of finding the particle will be non-zero inside the box, and 0 will be on the, you can say, boundary or the outside of it. So psi of 0 is equals to 0. Just putting the putting x equal to 0 in the equation, this, so sine 0 will be 0, b cos 0 will be 1, so b is coming as 0 here. So now we are required to find this, and actually this b goes to 0. Okay, now we will apply boundary condition again, one at x equal to L. So at x equal to L, if you will just apply, so what happens, b already went to 0, so a sine kl, so a sine kl equals to 0, so kl can be n pi. Okay, yeah, this is a general trigonometric, you can say, equation. So kl can be n pi, where n can be 1 2 3. Okay, then you can take the L. Okay, you can take the this L to the LHS, RHS. Then you have the Kn. Okay, just putting this Kn into the main wave equation, you get the solution. So simple. Okay, so you have to just apply. The main concept is you have to apply the, you can say, you have to use the equation actually at boundary conditions, that is x equal to 0 and x equal to L. If you just do this, you will be quite ready to get the wave function. Okay, the solution of wave function. Then we have also this particular result to determine constant an, because you can see here, just have a look on this. We got kn here. Okay, we got kn because for n is equals to 1, we have k as pi by l. So we can put k is equals to pi by l for n is equals to 1. But here we are discussing for n is equals to n. So for n is equals to n, we are defining kn, then this a will be an. Okay, this a will be an. So just we are not satisfied with a value of a, so we are just getting again trying to get the constant an. So here we will use the normalization of wave function, that is 1 is equals to the integration 0 to L sin x whole square and dx. Then we will just put the sin x value, this one here, taking this an square out of the integral, and then here you have to just use the simple concept here, that is sin square n pi x by L, that we already uh, obtained here. And then you have to change the limit from 0 to L to 0 to n pi, because actually now we are discussing in terms of the scale. Okay, so when you will just proceed through this particular you can say process, then you will get the an as root under 2 by L. Okay, so we made a change of variable in the third line here, that's the noticeable point. So here eta, this is called eta, that is n by x by L. So eta is actually n by x by L, and then we have just taken the d eta, and then we have just changed the limit. So eta is taken as n by x by L. So now we get the finally the equation for it, where initially we use the boundary condition to get that b is equals to 0, and then the kn and all. Then we use the what? Then we use the normalizations definition to get the an. Okay, so that's it. Now we will just discuss here this root under 2 by L. Okay. So let me clarify you once more. So this n square is there. Okay. Here we have taken this n as n pi x by L. Okay. So then what we did, we just substituted eta as n pi x by L. Okay, so sine square eta, and then we have L by n pi. This factor comes here. Okay. Into d eta. Why? Because actually here we have to take this, we have to change the limits. So from this 0 to L, we have to change through the eta to 0 to n pi, and then we get this an is equals to root under 2 by L. So this is actually the your discussion on the one-dimensional box. Okay, we have some more topics here, energy and all, so that we will discuss. Okay, so let me add some PPTs on the energy portion. Give me 2 to 3 minutes. We discussed already, I think, while discussing the Schrodinger wave equation about the energy and all. Yeah. So that's the same here also. So no need to repeat it. So this was our today's lecture on the particle in one-dimensional box. I hope you enjoyed this lecture and learned new topic. And with this, I'm just wrapping up this quantum physics. Okay, so we will soon meet with the new concept, maybe in mathematics. Okay, so till then, bye bye, take care, and see you soon in the next session. Okay, and again for the collaboration, you can email me at my email ID, that is 115@gmail.com, and then we can plan for the demo sessions, and then we can introduce you to the channel. This is still a growing channel. We have nearly 91 subscribers, but as you can see, my videos are not meant for the subscribers. As this video, and including all the shots, we have 80 total videos, including the shots, and we have the subscriber 91. So there is no any competition that if I'll get that. You see some YouTubers, they will say that if you will not make my subscriber 1K, 2K, 3K, I'll not start the live lectures. I'm still taking the lectures. So that's the difference. Okay, so education is not a business. First of all, it's a joyful duty to the nation, and that I enjoy. It's my passion, so I'm doing that. I don't need any validation from others that whether it is a good work or not, because as I feel and as I follow the philosophy that whatever work I'm doing, I'll do it as at the best work in this universe. So that I'm doing, and I'll do it until my last breath. Thank you so much. Okay, so bye bye, take care. For the upcoming lectures, I'll give a notice soon. Okay, and I'll plan for the more consistent lectures. Okay, thank you. Please do revise this particle in one dimensional box. This is very important. Okay, if you're serious. If you're not serious, then you can go. Thank you. I'm ending it in one, two, three. Bye bye.